So this is lab number 5, Faraday's Law. So in this lab, we're going to observe the effects of the Curly electric field created by a time-varying magnetic field and explore how that field can drive current in a circuit, exerting force back on that magnet as well. And then we're going to construct an experiment using a falling bar magnet and a tube of aluminum foil to observe it and compare our experimental measurements to those we compute using Faraday's Law in a Python model. So first, some physics principles we're going to need to know would be the magnetic field of a dipole formula and the magnetic flux through a ring with a known radius caused by that time-varying magnetic field, as well as Faraday's law that tells us about the EMF of that induced current, and Lenz's law telling us the direction of that current, as well as magnetic force, and Newton's third law and the superposition of forces. So for the experiment, we're going to use a roll of aluminum foil as a conductive tube and drop a bar magnet down the tube center and record it while it's falling using a smartphone camera. So using the video we made with the smartphone camera, we're going to scrub and find the time the magnet enters the tube, the time it exits the tube, and we're also going to need to measure the dimensions of the tube. So here are my measurements from the 5 trials of the experiment, and I found the average time it took for the magnet to fall through the tube was 2.072 seconds, and this is the magnetic dipole moment that I measured for my magnet using the magnometer app as well. And so for our Python model, we're going to first create some constants that we need, including the resistivity of aluminum, which is what the tube is made of, and some magnet properties, as well as the tube properties that I measured, and create a graph, add some numerical parameters about distances and thickness of segments we're going to simulate here, and then we're going to model the tube as a series of stacked rings along the y-axis. And so then we're going to create some computations in here. First, the magnetic field of a bar magnet, and then the derivative of magnetic flux with respect to time through each ring due to that falling magnet. And then we're going to also need to know the gravitational force on the magnet, and then we can use the magnetic flux formula to find the magnetic force on the magnet and add the gravitational force and magnetic force to find the net force. And then we're going to simulate that magnet dropping through the tube in a visual way as well. And throughout the simulation, we need to update the magnet's velocity and position, and also we're going to graph the velocity with respect to time. So here's the output of the model, and this is a tube that the magnet was falling through. And so here are the currents that were induced here. So the red is counterclockwise current and the blue is clockwise current. And we can find that by knowing that the north side of the magnet is pointed downward. And so using Lenz's law and the right-hand rule, we can determine the directions of the current there. And if we flip the magnet around, the current would go in the opposite direction. And so the output here says that the time in tube was 1.9 seconds, which is a little bit less than what I had in real life in my experiment. And that's probably due to air resistance and maybe some other forces present in the real world. And the velocity versus time graph here shows you the magnitude of the velocity decreases once that current is induced, so it's decelerating here, and then it kind of plateaus and the magnet then falls out at the end. So what if the resistivity of the aluminum was 0? How would that change the dynamics? Here the magnet would fall slower because the current induced in the rings would be higher, causing greater force on the magnet due to the tube. And then also, what if there were holes in the tube? The magnet would then fall faster because there'd be fewer current rings in the tube exerting a force on the magnet.